Bonding a water meter involves connecting the meter's enclosure to the electrical ground system. While generally safe, several potential hazards should be considered. Firstly, electrocution can occur. If the water meter is not properly grounded, a fault current could pass through the bond, potentially electrifying the water meter enclosure. Anyone touching the enclosure could be at risk of electrocution. Secondly, corrosion is a concern. When two dissimilar metals are bonded together, galvanic corrosion can occur. This can lead to accelerated deterioration of the bond and the water meter itself. Thirdly, ground loops can form. If there are multiple ground paths for the water meter, a ground loop can be created. This can result in stray currents flowing through the water meter, which can damage the meter or other equipment. Fourthly, interference with other systems can arise. The bond between the water meter and the ground system can create a path for electrical noise or interference. This could affect other sensitive electronic equipment in the building. Fifthly, damage to the meter can happen. Inappropriate or excessive bonding can stress or damage the water meter, causing it to fail prematurely. To mitigate these hazards, the following precautions should be taken. Firstly, use a proper bonding conductor, for example, copper wire of adequate size, designed for this specific application. The size of the bonding conductor must adhere to the requirements outlined in the National Electrical Code, specifically Table 250.102 cone. This table dictates the minimum size of the bonding jumper based on the size of the ungrounded conductors or the equivalent area for parallel conductors that supply the equipment. The bonding conductor should be copper, unless conditions specify otherwise, and should be installed in a manner that protects it from physical damage. Secondly, ensure the bond is made to a reliable ground system meeting all applicable codes and standards. The ground system should be verified for its effectiveness with a grounding electrode resistance that meets code requirements, typically 25 ohms or less as per NEC 250.53 ATWO, unless a two-point test reveals low resistance to ground. This ensures that fault currents are effectively dissipated, minimizing the risk of electrical shock. Thirdly, use a dielectric isolation washer to prevent galvanic corrosion between the water meter enclosure and the ground system. A dielectric union, or fitting, serves to electrically isolate the similar metals in the plumbing system, preventing the flow of current that causes galvanic corrosion. This fitting should be rated for the pressure and temperature of the water system and should be installed according to the manufacturer's instructions. Fourthly, avoid creating ground loops by ensuring there is only one primary ground path for the water meter. Ground loops can create circulating currents that interfere with sensitive electronic equipment, increase electromagnetic interference, and potentially cause inaccurate readings from the water meter. To prevent ground loops, ensure that the grounding system is a single-point ground, with all ground conductors connected to a common grounding electrode conductor. Fifthly, consult with a qualified electrician to assess the suitability and safety of bonding a water meter in a specific application. A qualified electrician can evaluate the specific electrical system, local codes, and the type of water meter to determine the appropriate bonding method and materials. They will ensure that all work is performed in compliance with the NEC and local regulations, minimizing the risk of electrical hazards and equipment damage. Bonding requirements may vary depending on local codes and regulations. It is crucial to follow all applicable guidelines to ensure safety and avoid potential hazards. Different municipalities and jurisdictions may have specific requirements for water meter bonding. These requirements can vary based on factors such as the age of the building, the type of electrical system, and local environmental conditions. It is important to consult with the local electrical inspector or building department to ensure compliance with all applicable codes and regulations. The grounding electrode conductor connects the grounding electrode to the equipment grounding conductor, the service equipment enclosure, and often the grounded conductor at the service. Its size is determined by NEC Table 250.66 based on the size of the service entrance conductors. For example, if the service entrance conductors are 2/0 aluminum, the minimum size for the grounding electrode conductor is number 6 copper. This conductor must be securely connected to the grounding electrode using approved methods such as exothermic welding, listed pressure connectors, or clamps. The equipment grounding conductor provides a low impedance path for fault current to return to the source, tripping the overcurrent protective device and clearing the fault. The size of the equipment grounding conductor is determined by NEC Table 250.122, based on the rating of the overcurrent protective device protecting the circuit. For example, for a 20 amp circuit, the minimum size for the equipment grounding conductor is number 12 copper. This conductor must be installed in the same raceway or cable as the circuit conductors and must be securely connected to all metal enclosures, boxes, and equipment. Supplementary grounding electrodes, such as ground rods or ground plates, can be used to improve the effectiveness of the grounding system. These electrodes must meet the requirements of NEC 250.52 and must be installed at least 8 feet apart. They should be connected to the grounding electrode conductor using approved methods. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. This includes checking the connections for corrosion, verifying the grounding electrode resistance, and testing the ground fault protection system. Any deficiencies should be promptly corrected to maintain a safe and reliable electrical system. Proper bonding and grounding are essential for electrical safety in commercial and industrial settings. By following the requirements of the NEC and local codes, and by implementing appropriate mitigation measures, the risks associated with water meter bonding can be minimized. Always consult with qualified professionals and stay informed about the latest codes and standards to ensure a safe electrical environment. It is crucial to understand that the effectiveness of a grounding system is influenced by soil conditions, moisture content, and the presence of corrosive substances. In areas with poor soil conductivity, such as rocky or sandy soils, additional grounding electrodes or ground-enhancing materials may be necessary to achieve the required grounding resistance. The use of ground-enhancing materials, such as bentonite clay or chemical ground rods, can improve the conductivity of the soil and reduce the grounding resistance. These materials should be installed in accordance with the manufacturer's instructions and should be compatible with the local soil conditions. The selection of appropriate bonding and grounding materials is also important to ensure the long-term reliability of the system. Copper conductors are commonly used for bonding and grounding due to their excellent conductivity and corrosion resistance. However, in certain environments, such as areas with high levels of corrosive substances, stainless steel or other corrosion-resistant materials may be more suitable. The use of dissimilar metals in the grounding system should be avoided, as this can lead to galvanic corrosion. When dissimilar metals must be used, a dielectric barrier should be installed between them to prevent the flow of current. The installation of bonding and grounding conductors should be performed by qualified electricians who are familiar with the requirements of the NEC and local codes. The conductors should be properly sized, routed, and connected to ensure a low impedance path for fault current. The connections should be made using approved methods such as compression connectors or exothermic welding, and should be protective from corrosion. The grounding system should be tested after installation to verify its effectiveness. The grounding electrode resistance should be measured using a ground resistance tester, and the results should be compared to the code requirements. Any deficiencies should be corrected before the system is put into service. Regular inspections and testing of the grounding system should be performed to ensure its continued effectiveness. The frequency of inspections should be determined based on the environmental conditions and the criticality of the equipment being protected. The inspection should include a visual examination of the conductors and connections, as well as a measurement of the grounding electrode resistance. The grounding system should be maintained in accordance with the manufacturer's recommendations and the requirements of the NEC. Any repairs or modifications should be performed by qualified electricians using approved materials and methods. Proper documentation of the grounding system is essential for future maintenance and troubleshooting. The documentation should include a detailed diagram of the grounding system, including the location of all grounding electrodes, conductors, and connections. It should also include the results of the grounding electrode resistance tests and any other relevant information. The documentation should be kept in a safe and accessible location and should be updated whenever any changes are made to the grounding system. In addition to the technical aspects of bonding and grounding, it is important to consider the human factors that can contribute to electrical accidents. Workers should be properly trained on the hazards of electricity and the importance of proper bonding and grounding. They should be provided with the necessary personal protective equipment, such as gloves and safety shoes, and should be instructed on how to use it properly. They should also be encouraged to report any potential hazards or concerns to their supervisors. Electrical safety should be a top priority in all commercial and industrial facilities. By following the requirements of the NEC and local codes, and by implementing appropriate safety measures, the risk of electrical accidents can be significantly reduced. It is also important to stay informed about the latest developments in electrical safety technology and to incorporate these advancements into the facility safety program. For example, the use of arc flash protection devices can help to reduce the severity of arc flash incidents, which are a major cause of electrical injuries and fatalities. The installation of ground fault circuit interrupters, or GFCIs, can help to prevent electrical shock in wet or damp locations. The use of insulated tools and equipment can help to protect workers from electrical hazards. By continuously improving the facility's electrical safety program, it is possible to create a safer and more productive work environment. The National Fire Protection Association, or NFPA, offers a wide range of resources on electrical safety, including codes, standards, training materials, and certification programs. The NFPA 70 National Electrical Code is the most widely adopted electrical code in the United States and provides detailed requirements for the safe installation and maintenance of electrical systems. The NFPA 70E Standard for Electrical Safety in the Workplace provides guidance on how to protect workers from electrical hazards in the workplace. The NFPA also offers training programs on electrical safety, including arc flash safety lockout/tagout procedures and electrical hazard recognition. These training programs can help workers to develop the knowledge and skills necessary to work safely around electricity. The NFPA also offers certification programs for electricians, electrical inspectors, and other electrical professionals. These certification programs demonstrate that individuals have met a certain level of competence in their field and are qualified to perform electrical work safely. In addition to the NFPA, there are many other organizations that offer resources on electrical safety. The Occupational Safety and Health Administration, or OSHA, is a federal agency that sets and enforces workplace safety standards. OSHA offers a wide range of resources on electrical safety, including fact sheets, training materials, and enforcement guidance. The National Institute for Occupational Safety and Health, or NIOSH, is a federal agency that conducts research on workplace safety and health issues. NIOSH offers a wide range of resources on electrical safety, including hazard alerts, research reports, and training materials. The Electrical Safety Foundation International, or ESFI, is a non-profit organization that promotes electrical safety education and awareness. ESFI offers a wide range of resources on electrical safety, including fact sheets, brochures, and videos. By taking advantage of these resources, businesses and individuals can learn more about electrical safety and take steps to protect themselves and others from electrical hazards. Always remember that electrical safety is a shared responsibility. By working together, we can create a safer and more productive work environment for everyone.